Welcome to the Watermarks Note Series. This is a suite of brief lectures describing some of the fundamentals in the fields of open channel hydraulics and river mechanics. Today's overview will highlight some of the basics of specific energy. We'll begin by developing a table for a constant discharge occurring in a channel of constant width. In this case, a discharge of 15 cubic meters per second and a channel width of 10 meters. A constant width channel could be observed in the field where a concrete channel has been constructed with vertical walls such that, independent of the discharge that occurs, the width of the channel will remain constant. Therefore, the only thing that would vary would be the flow depth. In this case, we'll vary the flow depth between 0.01 meters all the way up to 5 meters and increase the increment at 0.01 meter intervals. We can therefore calculate the velocity for each of these flow depths by applying the continuity equation, where the velocity is equal to the discharge divided by the width times the depth of the channel. We can calculate the velocity head, which is v squared over 2g, and finally the specific energy, which is equal to the sum of the flow depth y plus the velocity head v squared over 2g. If we look at the specific energy relationship, this is merely the potential energy plus the kinetic energy. Now, if we inspect the table, let's say for a relatively shallow flow depth of 0.03 meters, we'll note that this has an unrealistically high velocity for a natural channel of 50 meters per second, but in this case, what we want to point out is the fact of the preponderance of the specific energy is contained within the velocity head. If we look at the opposite end of the spreadsheet, let's say for 4.97 meters, we'll notice that the majority of the specific energy is retained within the flow depth. So let's plot this relationship and see what the attributes are. We'll notice that a parabola is generated where the upper limb of the parabola is subtended by a 45-degree line when the flow depth and the specific energy are plotted to the same maxima. Let's choose a random specific energy, in this case 3 meters, and we'll note that this intersects two potential arms of the specific energy curve, thus meaning that we can have two potential flow depths for one given specific energy. One that's large at 2.98 meters in this case, and one that's shallow at 0.2 meters. The third thing to note is the minima. In this case, what's referred to as the critical flow state. This provides a divider between the upper and the lower arms of the parabola. The upper arm is identified as a subcritical flow regime, where the velocities are lower and depths are larger, and the lower limb is what's referred to as a supercritical flow regime, where the velocities are higher and depths are shallower. Now let's look at a few of the other attributes of this curve. Again, replotting the curve that we've previously generated and choosing the same random specific energy of 3 meters, we'll have these two potential flow depths that may exist, one at 2.98 meters and one at 0.2 meters flow depth. These are what are referred to as the alternate depths. We can transition from the upper flow depth of 2.98 meters down to the shallower depth of 0.2 meters, but we must follow the specific energy curve for the given channel width and discharge. How could this occur in nature? Well, we may have a channel bottom at the lowest point, referred to as the thaw wig, that may transition from one given slope that is relatively shallow to a steeper slope. This transition slope will then generate a lower velocity with larger depth in the upper reach, and with the steeper slope generate a higher velocity and shallower slope in the lower reach. We've talked about transitioning from the upper to the lower flow regime or depths, but what happens if we go the opposite direction and trying to transition from the shallow depth to larger depth? This will be for a future lecture. What we're going to focus on here is what happens if we were to vary either the discharge or the width of the channel. So let's begin again by regenerating the same specific energy curve for our 15 cubic meters per second and 10 meter width. But now we're going to vary the discharge. And we're going to vary the discharge between 2 cubic meters per second and 40 cubic meters per second, generating 5 different discharges, and that's 5 different unique specific energy curves. How could this occur in the field? Well, we may have a precipitation event that falls over a given watershed, in this case, Kanakajig Creek watershed. Here, precipitation has occurred, which is in green, which is illustrated as a hyetograph, which is merely the distribution of precipitation over time. And eventually that water flows overland until it intersects the creek and eventually produces what's referred to as a hydrograph, which is simply the discharge in the channel over time. So now if we look at a series of different discharges, let's say 2 cubic meters per second, it'll produce the hydrograph response for those locations and the specific energy curve that's on the lower left corner. As we increase the discharges, as we observe them in the field, we will note that we're producing a unique specific energy curve for each given discharge. And again, remembering that for this case, the width of the channel will remain constant. We will notice, though, as we generate these curves, they progressively increase and shift to the upper right-hand corner. And if we plot the intersection of the minima of each of these curves, they will locus along a constant slope line as long as the width of the channel remains constant. Now let's examine a condition where we change the channel width and keep the discharge constant. Again, we're going to recreate the same curve for a 10 meter wide channel, and now we're going to vary the channel width from 2.5 meters, which is the curve to the upper right, and progressively increase to 5, 10, 15, and 30 meter channel widths, which is the specific energy curve that's related to that width on the lower left side. The difference when one inspects between the changes in discharge and changes in channel width, we will notice as the discharge increases on the left-hand graph, the specific energy curve shifts towards the right where the velocities would be higher for the given channel. Whereas in this case, for the change in channel width, the velocities increase in the narrower widths. Where would this condition occur in the field? Well, these are very unique and difficult locations to identify, but they can occur in bedrock channels where we can have radically large variations in channel width, although the depths vary radically as well. Where this more commonly occurs is when we identify meandering channels in the field on relatively sinuous channels, where we can identify the width on the bend compared to the width on the crossover or the riffles of a channel. They will vary, at least on the bends, by 30 to 50% larger than what we typically identify on the crossovers or the riffles. This ends